Okay, unlike previous lectures where I would say I'm going to work on grading the exam, I hadn't gotten around to like really starting grading it. I actually did put a lot of time into grading the exam this weekend. I'm not done with it yet, but I'm probably about like 60 to 70% finished with grading it. Generally, I think the averages are going to be, comparable to before, maybe even a little higher. I'm not sure yet, though. One of the things that, so I'll give you a couple data points. So, like for example, on the conceptual problems, the class average was like an 80%, which was pretty good. And for some of the later problems, there's a lot of students that are pretty much doing them like correctly, completely, just a few little, sign issues or values here and there. One thing I will say, though, about the exam is I think that if there's any one general piece of advice I would give to the class as a whole, it would be that some of the approaches on some of the problems are probably more involved than they needed to be. And that's not to say that you didn't understand or even that the class average is going to be bad. I don't think it is. I think that as a whole, I think you're going to do well on the exam. But I think the best example of that was problem 6, because that problem you didn't have to use any vector notation at all. And some of the solutions, there were cross products all over the place. And that didn't mean you did anything wrong. It just is taking a little longer to grade than originally expected. But again, I think y'all did very well. On the homeworks, this probably looks a little weird, what's going on here. So I think I might have mentioned this before, but what had happened on homework 5.3 was a boo-boo on my part, because I had an error in the solution. What happened on the solution was there was the problem 2 had a distributed load that went from 300 to 450, and on my solution I went from 300 to 400. So my TA had wrote me and said, so everybody got that problem wrong. And I looked at it, was like, oh, that's because my solution's wrong. So they have to go back and fix problem 5.3. I know my TAs are really happy with me about that. But that's why homework 5.2 and 5.4 are graded, but 5.3 isn't. But they're still chugging away at it. But the solutions are posted for all those assignments, so you have those. And 5.3 should be corrected. 6.2 is assigned today. That's an error. This should be 6.2 is due today. And 6.3 is assigned today. I'll fix that. Today what we're doing is we're starting our second structural analysis topic. So near the end of this course in statics, and as is the case with every statics course that's ever existed, there are typically 2 main tasks that a professor has in regards to introducing students to static principles as they relate to structural analysis. The first is to impart upon students the ability to solve a truss, which we've done that and gone through that 2 different ways. The second is the introducing to students the ability to draw a shear and moment diagram. I will go ahead and tell you that this is not the last time that you are going to see shear and moment diagrams, particularly for those of you that are taking me for Engineering 216 next semester. We will see shear and moment diagrams in there again. And if you're a civil engineer who is planning on taking me for structural analysis, we will really do shear and moment diagrams in there. So today's and Wednesday's lecture are really meant as introductions to the concept of shear and moment diagrams. We're not going to get really deep into the weeds of it, because we could really make the problems challenging and interesting. We could put internal hinges in the beams. We could do triangular loads and all sorts of weird things, and we're not. We're just going to keep it basic, because I just want you to understand the concept. If you understand the concept, you can pick up the details as we go along. So what is the deal for shear and moment diagrams? I have here that they're incredibly useful tools for civil engineers, but that's not entirely accurate. They're also pretty useful for mechanical engineers as well, because what they essentially represent visually and graphically is the internal force response inside a flexural element as a function of length. So for example, here's a somewhat funky beam. This is definitely more complicated than anything we'll do in this course. But if I have this particular beam, and let's say that's a hinge support or a pin support, that's a roller support. I propose to you that this is what the shear diagram looks like, and this is what the moment diagram looks like, okay? Shear diagrams, in a nutshell, are illustrating the change in vertical forces along the beam. That's kind of why we use the letter V to represent shears. And moments are representing the internal bending, the internal flexure inside an element. And they are critical to successful design. And I don't care if we're talking about beams in bridges or we're talking about support struts in vehicles or what have you. What these tell me as an engineer is what I need in order to size this given element. For example, if I'm looking at the bending moment diagram, I'm seeing a maximum absolute bending moment of 460 foot kips. So what that tells me as an engineer is I need to pick a beam, you know, the material properties, how deep the beam is, etc., such that it can resist a bending moment of 460 foot kips. Likewise with the shear, the absolute maximum value of shear is 46 kips. So it tells me what to design for. We need to be able to quantify those internal responses in order to size the element. And I've given you the example before. If I'm sitting here on this table and we take the samurai sword or lightsaber through the table right here, I'm going to fall on the ground. The reason is that because right here inside the table there are internal forces, internal shears, internal moments that are keeping me upright. What this diagram and what these two diagrams are showing are what are the internal forces and moments everywhere along the beam, not just the samurai sword or the lightsaber cut right here, but everywhere, okay? So this is a really valuable tool for engineers. It's also, at least for the problems that we're going to be dealing with, they're fairly easy to construct. Now, what I want to do is I first want to start by looking at our sign convention, because this is very, very important, okay? So I propose, so first off, as I mentioned earlier, and as will be the case for the rest of the semester, we are in 2D, two-dimensional land. No 3D problems. We're not going to worry about that anymore. More often than not, engineers, when possible, like to idealize their problems in 2 dimensions, and we're going to continue with that convention here, okay? When I cut a section through an arbitrary point in a structure, I propose that you're going to get at most 3 unknown components, okay? An unknown force in the x direction, an unknown force in the y direction, and an unknown moment, okay? Just corresponding to our 3 equations of equilibrium in 2 dimensions. Now, I want to just, I know I'm highlighting shears and moments, but I want to look at the axial forces, these letter P's, if you will. Notice how, so this is what you're seeing here in this upper image is if here's the table, right, and I've samurai sworded and lightsabered through the table, and I'm splitting it apart and looking at either end where I've cut through the section. Now, the P's, look what's going on here. If I was just looking at this diagram right here, about fell there. If I was just looking at this, would you tell me that that P is representing tension or compression? The letter P. Is that tension or compression? Tension. It's tension. It's yanking away from the section, right? What about on the other side? What's the P representing? It's tension, right? So on either end of the section cut, the force is of equal magnitude and opposite direction. Is everybody okay with that? And that has to be the case for equilibrium to be met. So like with the axial forces, where on this side it's going to the right and this side it's going to the left, we have to adopt a sign convention. Now I propose what most engineers do with axial forces is they consider tensile forces positive. The reason they consider tensile forces positive is because tensile forces tend to make the member longer. Like if I take a member and I yank on it, it's going to increase in length, whereas compressive forces tend to shorten a member. So we as engineers tend to consider axial forces that are tensile positive. So for axial forces, if tensile forces are positive, that's our sign convention. This is a similar sign convention for shears and moments. It's very important that we maintain this sign convention in our analysis. To be honest, I'm really not going to harp on this too much, and some of the graphical techniques that we correspond later are going to sort of have this sign convention built into it. I just want you to recognize that the graphical techniques that we're going to develop here in a little bit are based off a consistent sign convention. Whoop. All right. Now, our goal is not to cut a section at an arbitrary point, determine the shears and moments, and then cut again, and cut again, and cut again. That would be very, very tedious. Cutting a section is one way to determine internal shears and moments at a given point, but I don't want internal shears and moments at a given point. I want them everywhere, okay? So what that means is I want to develop a graph, you know, like an X and Y graph on a coordinate system. I want to be able to graph the shear along the beam. I want to be able to graph the bending moment along the beam. And that's what I mean by a shear and moment diagram. It's just a graph, okay? Now, instead of cutting sections all over the place, we're going to be a little bit more intuitive, okay? So let's consider this beam right here. Okay, so first off, there's a couple things about this beam. Here's a beam. It's simply supported. For the purposes of this derivation, it doesn't really matter whether or not it's simply supported, fixed-ended. That's not going to matter, and you're going to see why here in a second. But I do want you to recognize I've got a coordinate system right here. So we've got an X and Y axis right here. And the load, if you look at the load, I've got just this sort of random variable load, and I have it pointing upwards, and I have it pointing upwards just so that means that the load is positive. Now, before I advance through the next few slides, I want to be 100% crystal clear. I am not going to make you do this derivation on a homework or exam, so don't think like, oh, I have to understand every single step or it's going to, you know, everything's going to crash and burn. I just want you to kind of get the idea. So don't feel like there's any hyper stress on your shoulders to understand, you know, to be able to replicate this derivation, because I'm not going to make you do that. So what I'm going to do is I'm going to look at this beam and I'm going to slice out a small element. I'm going to investigate an element that's dx wide, right? Y'all remember from Calc 1 that dx is an element that has infinitesimal width, right? It's like itty bitty, right? Very tiny. So if I zoom into that differential element that's dx wide, here's what I got going on. So first off, I have a variable load. The load changes as a function of x, but I propose on this really itty-bitty tiny element that I can assume the load to be constant because it's pretty tiny. Now, what we're doing here is I propose that on either side of the element, so for example, on shear, according to this sign convention, we have an upward shear and a downward shear, but I propose that from one side of the element to the other, the shear changes. Like I've got shear, and then I've got shear plus some increment. I've got moment, and then moment plus some increment. What I want to try and do is capture what's that increment, what's that change in shear, what's that change in moment. And you can probably kind of see where this is going, because there's dm's, dv's, and dx's. We're into calculus land. Well, I'm going to take that calculus land and I'm going to apply some principles of statics. So for instance, if I look at sum of forces in the y direction going up, so I look at my free body diagram, what do I have? I got v going up, I've got v and dv going down, so that's negative. And as for my load, it's not w going up, it's w times the width. Like if I got 2 kips per foot over a distance of 30 feet, that's 60 kips, right? So it's w times dx. So I've got v going up, w dx going up, and v plus v dv going down. So plug and chug, solve it out, the v's cancel, and I get this. On the moment side, what I will do is I will sum moments, and to keep it simple, I'm going to sum moments about the right side of the element. So I've got, let's see, what do I have? I have m, that's negative because I'm considering counterclockwise moments positive. What do I have? V dx, I'm summing moments from here, v times dx, that's negative 2. I have m plus dm, that's positive on this side. I don't have to consider the shear because it goes right through the right side. But for this distributed load, what I have is the magnitude of the load, w dx, times the moment arm. And the moment arm from the centroid of that triangular load is dx over 2. And so when I do my algebra and I evaluate that out, I get this. Now what's going on? Why am I canceling that? If I take a really tiny number, let's be clear, dx is a very small number. If I take dx and I square it, what do I get? A really small number. So I propose that whenever you have these higher order terms, dx squared, we can cancel them. So go through and chug out my algebra, and I get this. These are some very, very simple but effective calculus relationships. I propose that the relationship between load and shear is that the derivative of shear with respect to x equals the load. Or if I have my loads and I integrate them, I will get the shear diagram. Likewise, if I have the shear diagram and I integrate that, I will get the moment diagram. Now, I promise you, we are not going to be breaking out integrals of x squared or anything like that, because, as I said, this is a graphical technique, and you'll understand what I mean by that here in a little bit. The long story short with this graphical approach that we're going to utilize is you do need to understand a little bit of a relationship between derivative and integral patterns. Let me give you an example. What's the derivative of x squared? Oh, you should know that one. What's that? 2x. Okay, let me ask you this. What is the derivative of x squared plus 9x? 2x plus 9. Okay, all right. How about, let me ask it a little more generally. If I give you a parabola, and I say take the derivative of that parabola, what's the graph of that derivative look like? A line. Does that make sense? That if I take a parabola and I take the derivative of it, I get a line. If I take a line and take the derivative of that, what do I get? What's the derivative of 3x plus 9? 3. It's a constant, right? So if I take the derivative of a parabola, I get a line. Take the derivative of a line, I get a constant. So what about integrals? What if I have a constant and I take the integral of a constant? What do I get? A line. If I take the integral of a line, what do I get? See what I'm talking about here? There's a pattern here. Okay? I propose that this pattern is very, very important. We're going to discuss this lecture as well as the next lecture, because it's really going to be kind of important on the next lecture when we start dealing with distributed loads, because we're going to go from this to this to this. But I think what's important is that you understand some basics about plotting. For example, is this a positive slope or a negative slope? This one right here. Is that slope positive or negative? Positive, okay? Make sure you are just good with that stuff. Remember that the derivative will tell you the slope and that the integral will tell you the area under the curve. If you understand that stuff, you're going to be doing pretty good. Our graphical approach is basically going to be integrating successive diagrams, but the beauty of the diagrams that we're going to be integrating is that they're all just rectangles and triangles. So there's no need to break out the squiggly little s and the dx at the end of it. All we have to do is just look at it and integrate the area under the curve by just, magnitude times distance. It's actually going to be pretty straightforward. And I think that the easiest way to explore these relationships is with an example. Now, our example is going to begin with concentrated loads. Okay? So we're going to handle two types of loads in this course. We're going to handle concentrated loads and distributed loads when it comes to shear and moment diagrams. Now, I propose that here's a section of a beam, and over here there is zero load. Okay? If I integrate 0, I get a constant. I get a constant function. So I propose that for point loads, our shear diagram looks constant, and our moment diagram follows that integral pattern one more time, and I get linear functions. So I'm going to be dealing with sort of shear diagrams that kind of look like stair steps, and moment diagrams that are just going to be piecewise linear functions. And the way to construct them is going to be very, very easy. For the shear diagram, we're basically just going to follow the concentrated effects to construct the shear diagram, and then we integrate that shear diagram to construct the moment diagram. But integration is just area under the curve, and these are just going to be a bunch of rectangles. So I think you're going to find this is really simple. We're going to draw the shear and moment diagram for this problem. Now, if you go back into your notes a little bit, we actually already did this problem. We already computed the reactions. We're going to do it again just because, why not? You could use some practice. But after we've done this problem, I'm going to ask some follow-up questions, and we'll see if the concept, if the understanding is following along with that. Okay. All right. Let me make this a little bigger so we can all kind of see what we're doing here. So, we're going to treat this like a start-to-finish statics problem. First off, I have a hinge support, pin support. How many unknown support reactions? There we go. I want one loud voice. Roller support. How many unknown reactions? There we go. So, you must not be a music major. Timing's off. I'm messing with you. I'm just messing with you. All right. 3 unknown support reactions, 3 equations of equilibrium. Tell me which one I can solve for right now very easily. AX is 0. There are no forces in the x direction, so AX is 0. All right. Tell me what to do. At this point, you should know. I've got AY and BY. Give me a strategy for solving these. Sum the moments at where? A. Okay, we'll sum the moments at A, and that will allow us to eliminate A as an unknown and solve for the reaction at B. So we'll sum the moments at A, and so what do we have? We have 20 times 6, 30 times what? 20 times 6, 30 times what? One voice, come on.
15.
There we go. Somebody, all right. Somebody else. 18 times what? There we go, 22. Are these positive moments or negative moments according to our sign convention that we've adopted here? Negative. Let me move this down a little bit because I'm going to run out of room. And plus BY times 30 is 0. So 20 times 6 is 120. 30 times 15 is 450. 18 times 22, I had to cheat on that one a little bit. That's 396. So that and that and that sum up to give you 966. That's negative. Is that, did I do that too quickly, or are we okay with that? We should be good given that we've already done this example. That should be quick and that should be okay. So how do I solve for the remaining unknown? Sum the forces in the y direction. So AY plus BY minus those 3 loads. And let me drag that down. You'll see why I stretch that here in a bit. So 20 and 30 is 50, 18 is 68. So AY plus 32.2 kips is 68. is that. That should be easy, right? Hopefully by now, that doesn't need much explanation. If it does, do not hesitate, do not be shy. Any questions? Okay. All right. Do you need a sec, or am I good to scroll down? Okay, we'll take that as a yes. All right. So here's my beam, and I stretched it a little bit. Okay, I stretched it because I didn't want this to be all sandwiched on my my computations. Now I'm going to write that and that, because I want those here for what I'm about to do. Now, whenever you draw shear diagrams, there's no rule that says you have to do this, but it is typical that what you do is you draw a series of vertical guidelines so that you can line up what you're doing with what's on the beam. So what I'm going to do is I'm going to sort of like use my pencil here and sort of draw these dotted lines going down. Okay? And the way this works is the first thing that you do is you draw the shear diagram. Do the shear diagram first, then the moment diagram. That's why this topic is called shear and moment diagrams. Okay. Now, what we'll do is we'll say that this is the shear diagram, and we're going to say it is in kips. Now, all the numerical values that I put on my shear diagram, I'm just going to put numbers because I've already indicated the units there. Okay. Now, the way shear diagrams work, or the way that they should work, is that you start at 0 and you end at 0. So over here on the left, I'm going to start at 0. Now, the way that a shear diagram works is that you are integrating the load diagram. Now, how do you integrate a load diagram with a bunch of concentrated loads on it? Simple. You do what the beam is telling you to do. So watch with me. I'm here at 0, and the idea is to start here and work your way over. So I'm at 0, and what's the first thing I see? I see this 35.8 kip load. And so it's saying, Greg, go up to 35.8. Okay. I'll go up 35.8. What is on the beam between here and here? Nothing. So I go over. Greg, go down 20. Okay? I'm at 35.8. I go down 20. What's that put me at? No. That's a great question. No, I'm at 30. I'm at 35.8, and I go down 20. If I'm at 35.8 and I go down 20, what's that put me at? 15.8. Now, nothing. Greg, go down 30. My first name's Greg, by the way. All right. So I'm at 15.8 and I go down 30. If I'm at 15.8 and I go down 30, what's that put me at?
14.2.
Not 14.2. Negative 14.2. So this beam is very demanding. It's telling me to go down to negative 14.2. Nothing. 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 Greg, go down 18. So if I'm at negative 14.2 and I go down 18, what's that put me at? What was that? Negative 32.2? No change, no change, no change. Bam. What happens here? And I go back up to what? That's a shear diagram. It's that simple. It's that simple. Why do you think shear diagrams should start and end at 0? Because of statics? Well, that is an actually very accurate answer. I propose a more accurate but maybe more specific one, is because the sum of the forces in the y direction must be 0. But you're not wrong. You're not wrong. I want to stop for a second and see if anybody has any questions. Now, let's think about some things. In order to draw the moment diagram, we must integrate this diagram. Now, this diagram, mathematically, is a series of constant functions. So the moment diagram should be a series of linear functions, right? Let's see if that bears out. Now, but first we got to integrate. What does it mean to integrate? It means to find the area under the curve. Let's see if we can do that. Let's start off with this region right here. What is the area of that box? Do I have a second on that? Do I have a second on that? Okay. What is the area of that box? Do I have a second on that? Okay. What about this box? Yes, negative. And what was the answer? Second. And this box. Second. Now, somebody add these up. Huh, interesting. 0. It's almost as if the sum of moments equals 0. Because it does. The moment diagram is the integral of the shear diagram. The moment diagram must yield 0 as well. That is 100% correct. What does the moment diagram look like? A series of lines. Here's what it looks like. I'm going to scroll down a little bit. Moment diagram, foot kips. All right, let's see what happens. We start at 0, end at 0. Now what we're doing now is paying attention to the areas. Now, I start at 0, I increase to 214.8. Calculus tells me that if I integrate a constant, I get a line. So the diagram is a line from here to here. Now, if you're really paying attention, what's the slope of that line? That's exactly right. How did you get that?
I read the number at the top left.
That's right. It's sheer madness in here. Okay. The slope of the moment diagram comes from the shear diagram. Okay? Now, what do I do from here to here? I'm at 214.8, and I must increase by 142.2. What does that put me at? $357. And the slope of this line is 15.8. So, hold on. Graphically, does this look right? These are both lines with positive slope, but this slope is less than this one, right? Well, that shear is less than this one. Now, what happens from here to here? I drop down. How much do I drop down? 99.4. If I'm at 357, drop down 99.4, what's that put me at? And so that means that's going to drop down to 0. Now, we're not done because I got some other stuff I want to look at with this problem. But before we do, I want to know how this is. Any questions? Does this make sense? Have I lost you? Somewhere in between? Where are we at? Okay. I want to look at this question that was posed at the top. After we've finished this example, can we use the diagrams to determine the internal sheared moment at a point 12 feet to the right of A? And does this answer match what we compute by cutting a section? So, let's see something. 12 foot to the right of A would be like a cut right here. We'll call this section 1-1. Right? If this distance is 12 feet. You okay with that? Now, where would that be here on the shear diagram and the moment diagram? That'd probably be about like right here. And I don't know, maybe right here, which by the way, what's this distance here? If it's 12 feet from the left support, what's that distance? 6. So, would you agree that the shear at the cut is positive 15.8 kips from the diagram? Would you agree with that? I mean, that's what the shear diagram states, right? Okay, now how do we determine the value right here? Would you agree it's got to be between 214.8 and 357? maybe what we do is we say the moment at the cut is 214, hold on, 214.8 foot kips plus, was that 6 feet times 15.8? Sort of like an MX plus B sort of thing. What is that? 309.6. Does that value kind of make sense? It's just linear interpolation. Is that okay? Is everybody okay with that? Now, does that match our basic instance of equilibrium, our basic statics computation related problem? Well, let's see. Let's see what happens. All right, let's cut a section at x equals 12 feet and see what happens. Now, remember with trusses, when we cut a section, that there's something advantageous or strategic about picking which direction you want to look? Let me ask you a question. Now, keep in mind, AX is 0, so we really don't have that to consider. When I cut a section, would it make sense to look left or look right? I think it makes sense to look left. There's less stuff going on. I only have 2 loads over here. I got 1, 2, 3 over there. Let's cut a section and look left. Let's see what we get. All right. So here's the beam. Here's where I samurai sorted or lightsabered through the beam. I have a support right here that has a load going through it of 35.8 kips. I have a load right here of 20 kips. This dimension right here is 6 feet. This is 6 feet. Is that fair? Is that like an adequate representation of the beam on that end? Now, what did I say would happen if I'm sitting on this table and you samurai sword or lightsaber right through here? I'd fall. And what did I say would happen to your grade? I actually didn't say what would happen, but I'm keeping that to myself. The reason, it probably would. The reason is that because inside the beam, there are internal responses inside that table that are internal responses that are keeping this upright. I propose that those internal responses should be drawn like this. Why am I drawing the V going down? Because according to our sign convention, when I cut a section and look to the left, I'm going to go back to my slideshow because I want you all to see that. When I cut a section and look to the left, downward shears are positive. When I cut a section and look to the left, moments counterclockwise are positive. So I'm drawing these according to their positive sign convention and seeing what happens. So watch this. Let some forces in the y direction taking upward forces positive. 35.8 positive. Minus 20 negative because it's going down. Minus V is 0. What does V have to be for that equation to be true? What sign? Well, hold on. 15.8 kips minus V is 0. Like V has to be a positive number. Does that make sense? Does that match what we got up here? Yeah. What about the moments? Now what I'm going to do is I'm going to sum moments, and I'm going to sum moments at the cut. I'm going to sum moments at the section cut. So 35.8 times what? Times 12 from here. If I sum moments from there, 35.8 times 12, is that positive or negative? What was that? Somebody help me out. Well, but hold on. This is look at our sign convention. Negative moment. Then we have positive 20 times 6. Now, do we have to consider the V if it's going right through the section cut? No, but we do need to consider the M, okay, because the M is a moment. What I'm going to do is I'm just going to add M. No section, no distance, no nothing, because it is a moment. All right? Moment is defined by force times distance, but this is already a moment. I don't need to multiply it by some distance. Let's see what happens. What did you say 35.8 times 12 was? So M is what is 429.6 minus 120? Oh. I don't know about you, but does that match what we came up with before from the moment diagram? Well, by golly gosh gee, yes it does. That's a marker case drop moment. Or mic case drop, I meant. My mic's expensive, I'm not dropping it. What do you think? Does this make sense? Okay. What we're going to do next time is we're going to take this problem and we're going to deal with distributed loads. Now what a distributed load is going to do is a constant load. So a linear shear diagram and a parabolic moment diagram. But I got some graphical tricks for that one too. That's all I have. I will see you all on Wednesday.